today we would like to show you the recent work we've been doing at Takeda, enabling self-driving labs for synthetic molecule process development. But before jumping on this self-driving lab topic, I would like to give you a bit of background, of who we are and what we do and why we are pursuing this self-driving lab approach. So first, a bit of history about Takeda. It was founded in 1781. So it's quite an old pharmaceutical company with the HQ in Tokyo, Japan. It's one of the top 20 pharmaceutical companies with around 50,000 employees. And the therapeutic areas include oncology, rare diseases, plasma, vaccines, neuroscience, and gastro. Inside Takeda as a whole, we are part of the synthetic molecule process development, or SMPD, which is a process chemistry and engineering group located within R&D. We have around 100 FTEs in two sites, one in Cambridge, TMA, and one in Sonnen, TISO. And we only focus on synthetic molecules. So from all the prior pipeline, we will tackle the synthetic molecules one, which comprises small molecules, peptides, and oligos. And our work spans from early process development to process optimization and tech transfer. And we support this pipeline by finding new routes, so improving those routes so they can be transferred for clinical trials or manufacturing. We scale up some existing routes to provide materials for clinical trials, and we also do tech transfer to our manufacturing partners. And inside SMPD, we have our high-throughput and automation team, so we are embedded into the process engineering group. It's a relatively new team. It's less than 3 years old. And prior to 2022, there was no dedicated high-throughput or automation group at SMPD, only some isolated SMEs and equipment, with most of the work being externalized. So all of that you are seeing today has been developed in a bit less than 2 years. So it can be done. Then our team, right, aims to provide support to all global SMPD, and our focus areas include the main workflows, right, of our team, which are solubility, crystallization, and lipid extraction. We obviously do a lot of reaction screening and optimization. And in addition, we do some custom automations and some robotics projects that you will later see. And this is our team. So it says myself, then we have Andrew Kukor, which is an automation scientist, Dimitrios, which is our robotics engineer, Buta-san, that is the Japanese side of our automation scientist, and then Philip Tran is our newest robotics engineer. If you've seen our new labs in Cambridge, we have two differentiated areas. So we have the main high-throughput labs around the Unchained Labs family of tools. So we have here 4 juniors and 1 OSR. They are in a set of 2, so we have 1 powder junior and 1 liquid junior and duplicated, and they are inside a custom-made isolator, as you can see here on the left. And then we also have a robotics development area where we carry out some custom integration projects ourselves. So in the image on the right, you can see a dual-arm Yami in a Pentium frame. And this lab is currently being replicated in our site in Sonnen. And one of the beauties of this workflow is that once you have everything done, even it has taken us 2 years to reach this state, now we can very easily replicate our labs in our other sites, because we have all the knowledge and the know-how. So, a bit more of background on our historical problem statement and why we are trying to do what we do is that in the past, process development, and I think it still is very labor intensive, right? You have to do a lot of trial and errors, a lot of screening optimization efforts, and they were typically done in vials with the DOEs being experience driven by our scientists. And this resulted in SMPD being heavily outsourced because we didn't have the numbers to run all of this internally. Then if you outsource some of this work, often we have no clear understanding of the methodology employed by our partners. So how many samples they were evaluated, what certain variables were selected or discarded. You typically just receive a report with a few slides with the best performing candidates. And of course, the data is not there, right? You don't have typically access to all the data, from the analytical data to the process data of the reactors. And then one of the issues that we have, and also this is, again, if we do internal, it's a bit minimized, but it also happens that after we complete a project, the data is not stored in an internal databases, right? The knowledge is lost. And typically we duplicate efforts across projects. So unless we have a scientist that joins a similar project where they have faced a similar issue, we typically have to start from scratch. And on top of that, we are a relatively lean organization with not so many contractors, FTEs to run internally all the required screens in the standard manual approach. So if we want to change and shift how this works, our solution was what we call the self-driving data-rich HTE that we are trying to apply here. And now we are going to dig a bit more on this workflow that I will explain point by point. So here you can see a scheme of how we envision this workflow, what we are trying to build. So let me put the pointer. So this is a closed loop, multi-generation, self-optimizing workflow, but the main difference, right, is that it's not just the closed loop, but we start, the way we envision it is that we start in our ELN, in this case mathematics, where a scientist introduces a reaction, in this case, for instance, that they want to optimize, and then that reaction, which is just the smile codes of your product, your starting materials, etc., right, that gets translated into a reaction database where we have all of our prior knowledge, and there is a sort of retrosynthesis tool, although it's more a parameter recommender tool, that looks at that reaction database, at all of our prior knowledge, and then it's able to tell us if we have done something similar in the past, and more importantly, what parameters should we vary in order to optimize these reactions. Because most of the time when we are doing reaction optimization, we tend to use the same basis, the same solvents, the same catalyst, and we can have the best closed loop with the robotics, with everything in the world. But if we constrain our parameter space and then we left out some of the catalysts, some of the bases, some of the solvents that do actually work, we might be discarding some pathways that do actually work, but we simply are not able to optimize them, because here in the first step, what we are doing, when we are setting the boundaries, right, our parameter space, we are missing some key elements. So this prior knowledge coupled with all this retrosynthesis is where we try to minimize that in order to have a proper data-driven DOE, not just experience intuition-driven DOE. Then once we have that, we need to translate that into an automated reaction screening, in our case with the ACDLabs family of tools. We are also working in the automated consumables handling, because this is also something that typically it's overlooked. And if you run this 24/7, you will start to generate a lot of waste that you don't want manually to take care of. So we are also working on this side. Then we have the data-rich analysis. So we call it data-rich HTE because it's not just we take one sample for HPLC. We can take HPLC, but we can also take Raman, we can take Vision, and we can also take XRD if needed, right? If you are doing some crystallization, that will be the same loop, right? So it's more than just HPLC. Then we need a way to automate the data collection and visualization. That's where Catalyst kicks in. And then we also need to send this data to our AI optimizer, right, to predict the next generation. What should we test next? So that's where we are using Itinerary for. So then we can carry out this loop 3, 4, 5 times until we reach the maximum. And this is our standard business practice. So we don't do factorial DOEs anymore. We always go through this closed loop workflow, and it has been demonstrated to be really, really robust and efficient. But in order to be successful in this approach and have a paradigm shift, we need a smart combination of hardware and software. This is not just I'm gonna buy a few robotic platforms and alas, all my problems are solved. No, you need to also look at the data automation to remove all the bottlenecks, like analytical data process or software hardware connectivity, because here we are looking to end-to-end lab automation. So it's a smart combination of both. And most of the times the data automation it's overlooked because it's it's under their scenes, right? And it's not something that you see in the lab where you go to do a tour, right? You see all the robots, but not all the data connectivity that needs to be in the back for this approach to really be successful. And just to give you, one example of the integrations that for our workflow we need to have. So it's quite a lot of software layers between the physical and digital automation, with a master scheduler on the top. So we start with this retrosynthesis database that predicts the conditions. Those conditions need to go to Catalyst to build the reactant tables. Then those tables goes to Itinerary. Itinerary produces the first generation of samples to be evaluated. Catalyst translates that into the ACDLabs robots. They perform the experiment. Then we have the mobile robot that moves the samples to the UPLC. The UPLC does the analysis and goes back to Catalyst for processing. Then Catalyst sends that information to Itinerary to predict the second generation, then back to Catalyst, right, to create the new unchained file. And then we have the mobile robot here transferring new plates and removing all plates to the juniors. And on top of this, you need a master scheduler that's able to trigger all of this autonomously, right? In our current state, we are almost there regarding the integration. So you can see that only a few of them are being developed, and we are also developing the master scheduler. So it's a journey, and there is a lot of very small tasks that need to happen. So now we are going to dive a bit more on both sides, in the physical automation and in the digital automation. So for physical automation, the first approach we took, right, was to standardize the size and format of all of our screens, moving to bigger formats and lower throughput, 24 by 4 ml, instead of the standard HT practice of 96 watt plates. And we not only standardized the plate format, but also the positions in the robot deck, right? So we will always have the solvents in the same positions, the reaction plate in the same position, the caps in the same position, because this means that we will have less errors with the robots. And we can, by applying this standardization, it's much more easier for us to reach this autonomous self-driving loop. Also, in this lower throughput plate, we can gain confidence in the data, right? Because we scale up 10 times to reduce manipulation errors. We can overcome the loss of throughput, so we don't care anymore about big format plates, because we are using this AI guide optimization with the itinerary algorithms from one generation to the other. So this means that despite using a smaller format, we can more efficiently explore the parameter space. We can sample several times without disturbing the reaction, so typically we sample 4 times. Now we can fully automate the workflow, leveraging mobile robotics, as we will see, and then we can do a more data-rich despite being SD workflow. So we not only take HPLC, but also images, as you see here, and also we have non-contact Raman that we can take in the chain by moving the vial to the Raman. So we have a lot of information for each data point, not just a hit. Then, this standardization is what has allowed us to automate the workflow with the ACDLabs robotic platforms. So this is what I described, right? So we start with the powder dispense, then we do the capping, then we do the liquid dispense, then we incubate, then we can take an image of the vial, then we can also measure Raman and non-contact Raman, we can filter if needed for the sample prep, then we do HPLC sampling, and then we can also prepare in the junior these XRD Kapton plates in case we are doing some salt screening or crystallization. Then we have also developed a solution to close the physical workflow with a mobile robot looking to transfer the plate across the different juniors and the waters, UPLC, and with this integration, we will be able to almost double our throughput, because what typically happens is that when we start an experiment, right, we start it early in the morning, then we start the powder dispense, the liquid dispense, the reaction, and typically the reaction ends around 2 to 3 a.m. in the morning, right? So then you need to wait to the next day, go take that plate, just move it to the analysis, and then analyze the full plate. An analysis of the full plate typically takes also a few hours, so then you are basically losing that second day. While if we have the mobile robot, by the time we go back to the lab, the analysis is done, right? So we gain this extra day, right? It's like almost doubling your capacity with a very simple movement. And in our particular case, it's a mirror base with a UR5 arm assembled by Enable Robotics. And here we have a video that you will see the robot in our lab. So this is the isolator where we have the two juniors, the powder junior in the left, the liquid junior on the right. So here you can see the mobile robot opening the isolator. Door is a normal door, so it's opening like a human will open it. Then we have there the HPLC sample with a rail that goes out after the reaction is completed. So it will pick the plate, move it to the base, and then close back the isolator. We have also on top of this anti-chamber nitrogen and vacuum limes, so we can minimize the air contamination of the chamber during operation. But it also is not very, we have seen that it doesn't affect much our processes, because by the time the samples are analyzed, right, and you need to run second generation, it takes a few hours. And in that time, it has been regenerated to the specs. So now the mobile robot is driving around the lab. It's looking for our analytical instrument, which is this water UPLCMS with the automation portal. It will read the QR code to position itself a bit better. And then it will take the plate, put it in the portal, and then trigger the analysis. After the analysis is done, all that information will go to Catalyst and then to Itinerary. We will create a second generation, and then it will run autonomously in the lab. So you will see now. Yeah, that it's taking the plate for analysis, and then the robot simply goes back to the base for charging. So this is the physical automation, right, around the ACDLabs family of tools, the mobile robot, the automation portal of the waters. Now we need to look a bit more about the other side of the things, right, the digital automation. And as I actually mentioned during the whole webinar, that for us it's crucial, because in order to minimize the bottlenecks, we had to do something, right? Something that was not done before, and we found this solution in the form of combining Catalyst and Itinerary in a full integrated platform. This means that now we can generate the ACDLab robotic files that you see here on the left with the reaction plate, the analysis plates, all the maps in a few minutes. And you don't need any prior programming knowledge. You don't need to know how to do anything in the Unchained software. You don't need to know any machine learning software to operate the Itinerary platform. And Catalyst is also very intuitive. So, anyone with some minimal training should be able to run this workflow, and in order to demonstrate it. So I have here a recording. So it's a real recording of how it takes to run an experiment from scratch using this new integration, right? So we start in Catalyst as we decide, and here we are just adding some information of your experiment. So your department, your site, the purpose, the project code, it's a reaction, and that's it, right? So you can also save your experiment name. So this is just like creating an element, right? So it's the same. Then you go to your reaction scheme, where Catalyst has a very nice material database. So you can, in this case, for instance, we are trying to mimic that we are doing a coupling, right, reaction. So you can select a bunch of ligands that appear in the database, and then just drag and drop them to the reaction, and then we will do the same thing for all the elements, right? So we are also going to add some solvents for this process. So yeah, butanol, filter butyl ether, etc. So nitrogenous solvent. So we have them there. Then let's add also some bases. to the reaction. So it's just, again, dragging and dropping, simple. Then catalyst. So yeah, we can add palladium acetate and chloride to the mix. So you can see that we have already started to add quite some variables here, right? If we want to optimize all of these conditions. Then for the starting material, yeah, we are just going to do a couple of mock molecules, and same for the product, right? This is just for demonstration. Okay, so now that we have our reaction scheme, we move to the other side, right, which is the experimental layout. And here is where you define that your reaction plate, and here appears, right, as I said, we do add 24 4 ml well plate. And the only thing that you need to add is your starting material or your limiting reactant to the well, because all the rest of your compounds, right, will be calculated based on that. And now what we do is we select the parameters that we want to vary, right? So we want to vary all the bases as a discrete variables in equivalence from 1 to 3 with a stride of 0.4. And this creates that factor, right, in the DOE. Then we do the same with the catalytic agent when we want equivalence from 0.2. And this is uniform. Then you can do also ligands, right? And they can be continuous, they can be discrete. You can change the units. Typically, we use equivalence. And lastly, I think we have the reactant, right? You can also evaluate, okay, for my co-reactant, I want to study different equivalents from 1 to 2. And we typically also use discrete with a stride of 0.25 and in equivalence. Then last but not least, it's the solvents, right? So we want to also evaluate those solvents. So these are in milliliters and 1 milliliter. So now we have here all of our factor. We save it, and here is where the integration starts to kick out, because we are going to send this factor list with all the material classes, with all the information that it's in Catalyst to Itinerary by just pressing a widget. So now you can see that the Itinerary platform automatically opens it up, and it creates a workstation with already on it all the parameters that we want to vary, that we specified, right? So the base equivalence, the catalytic agent. So we just need to add now the parameter that we want to maximize, in this case, the peak area. And then we create a template, which is very simple. That is, it just guides you step by step. So you will see how quick that is. So you create the new workstation that's been done by the integration. You see here, everything that you want to vary. Then we have we want to maximize the peak area. Next, we can select the optimizer. So this is a very nice thing from Itinerary. You can select whatever optimizer you want. Our batch size is 24. Then we click next, and then we run the campaign. So I think the video is to the next slide. Yeah. So then you just launch the campaign. You can put whatever name you want. You can also preload data. So that's a nice feature from Itinerary, that if you have past data, you can use that data, so you shouldn't start from scratch. And here you can see that we have created an optimization reaction with all the conditions that came from the Catalyst integration. And I think it's been 5 minutes, something like that, right? Where we have been able to have all these measurements. So these are all the points suggested by the Itinerary algorithm. And now we go back to Catalyst, go to AI optimization, click optimization with Itinerary. And what will happen is that Catalyst will read those conditions generated by Itinerary, and then you can simply add reactions to container, to the reaction plate one, you select all, and this is beautiful. It's amazing that the well is automatically filled with the composition suggested by itinerary. Before, we had to do this manually, and it took a lot of time for us. And now the final part of the integration is where we are generating the library studio file for the Unchained Lab robots with just 2 clicks, right, that you have seen there. So this is to generate the file that the robot will use to start, and it will have the same plate, but in the Unchained Labs format, ready to be run. So this means that anyone with no need of prior knowledge, programming, machine learning, even familiar with the Unchained Labs system, now, thanks to the integration, so this is the Unchained Labs file that has been generated, it's able to run these AI-guided workflows, right, very, very simply. And now, in a few seconds, the file will open. Then we will move to the next section. Yeah, so here you have the Unchained Labs file, with all the maps, all the recipes, and I think I opened it twice. So this is what we will run in our juniors. So you can see how nice this integration works. Then we will have the analysis, right, that will come here at the end of the workflow, and we will send those analytical data back to itinerary to predict a new generation. So all that big area, then you send it to itinerary back, and yeah, there you have it. So this is really an amazing integration, and prior to have this, we have to transform the data into different formats, right? We were always working with Excel files to do transformation. So we add the materials in Catalyst, but then to fill the wells with the data provided by itinerary, so we had to create an Excel file like this, with a lot of manual calculations. Then we also needed to add those to the Unchained Labs. So it was one simple set of conditions that needed to go to Catalyst, to itinerary, and to the Unchained equipment, and all of them in different formats. We had to do a lot of manual calculations, so it could take us 4 hours to have everything ready for a simple reaction like the coupling that you are seeing here, right? So, but now it's just a matter of meters. We haven't used an Excel file to do these kind of things since then. No need at all. Now the last part of the presentation is it's just a case study showcasing all of this, right? To show you that it really works and we are actively using it. So the request is simply the example is a very simple backward reaction in the frame of a pipeline LCM project to replace the current reaction, and we didn't screen here a lot of parameters, right? Because we had some background information, but even 6 bases, a few base equivalents, 6 pre-catalyst, a few pre-catalyst equivalents, and 6 solvents. That's over 4,000 combinations. So if you want to do that in a manual way, where you have to screen everything, that will take you quite some time, right? And in our approach, this optimization was done in about a week, in comparison with the 1-2 months of back and forth that will take, with the manual external approach. So we already see here some big wins in time. And looking at the results, this is from Catalyst, the data analysis. So here you can see on the top the heat maps, which it's just the product peak area in different colors with the color and the scale on the right. So red a bit of product, orange more, yellow more, and green lot of products. On the bottom we have the pie charts, which is the peak area percentage composition for starting materials and products. So obviously more green, more product. And here you can see that on the left we have first generation, second generation, and third generation. So you can see that the AI algorithm of itinerary and our self-driving approach really works, right? So from the very first plate, where we have a kind of a random design, then to the second one and to the third, we start to see more and more green, right? And this is what we typically see. And it's not just that. We also have some very powerful visualization tools. So this one we liked a lot. It's the parallel coordinates graph, and each of the lines represent an experiment that we have done. So one of the conditions, using a base, a pre-catalyst, a solvent, base equivalence, pre-catalyst equivalence, and then the results in peak area, and the color represents how much peak area in this case have for your product, right? So you can also filter them, and this very quickly help us to tell, okay, we have potassium acetate and carbonate, and especially BINAP is the only catalyst that works for this reaction. We can use the uramyl alcohol or toluene. We have some freedom in the base equivalence, but we need relatively high catalyst loading. So, all of this information we can get from the data analytics embed into the Tinari platform. And also another one that we like a lot is this map, which it's a 3D, it's a 2D map, a multidimensional map converted into a 2D representation of all the possible combinations that are in the parameter space, being the green points, the one that have been evaluated in the campaign, right? And here, what we would like to see is that this is very important for us for a scale-up, because what we don't want is isolated maximums. For instance, like this point in the corner or this point, right? We want to focus in areas that are here, where you have several points, with good performance, because when you have to do a scale-up and the transfer, you don't want to take the risk of being in this area that you move a bit your conditions and then the yield drops drastically. So this is also a very powerful tool for us. And then lastly, another thing that we do is we tend to do a scale-up of the best predicted reaction conditions by combining the reactol and catalyst to confirm our findings and derive kinetic models. And this step only ends 1 or 2 days of the workflow. So we can get all the data from the 5 reactors and build the kinetics again in 1 or 2 more days. So we can provide a really good package of data in a bit more than a week. So summing up everything that we discussed today, right? So with the new emerging technologies, I think high throughput can be much more than just exploring a few conditions with a factorial DOE and hoping for a positive result hit. But however, developing this data-rich self-driving lab requires a lot of hardware and software integrations that sometimes are not easy to develop. And to reach this state, we have combined several commercial tools, like Chain, Catalyst, and Tinari, with some internally developed solution to fill the technology gap like Mobile Road, right? But I think the integration presented here is a great example of how the smart combination of these tools can really accelerate the workflow, and you can see, that especially to bring down the knowledge barrier, right? You don't need to be an expert to run these tools. And while this is not an easy path and has taken us 2 years to reach our current state, we have now the tools in-house, and we can easily carry out this AI-guided closed-loop optimization workflows, being much closer to our end state of truly unsupervised autonomous process optimization workflow. I think that's all I have. Thanks everyone for your attention.